You're the master of radio frequency technology. You understand everything there is to know, right? Meaning that you could take what you know to this point and go out and deploy an enterprise-level wireless network. So what does this mean when the antennas look like this? What does it mean when the antennas are changing their focus? Do you understand polarization, gain, beam width, free space loss? Probably things that you've not yet addressed in your learning of wireless LANs. What does it mean when you see that wireless access point sitting on the desk and the antennas are pointed together? What is it actually doing? What effect does that have in your space that you're trying to wire for your wireless networking? What we've got to understand now are some of the frequency principles of antennas and how they work, the polarization of antenna, and proper installation. There are several concepts that are essential knowledge when implementing solutions that require radio frequency antennas. Polarization, the gain of the antenna, the beam width, even the free space path loss. These are a list of absolutely positively must-have fundamentals that would allow an administrator to really understand how wireless LAN equipment functions over the wireless medium. A solid understanding of basic antenna functionality is the absolute key to being able to move forward in learning more advanced radio frequency technologies and concepts. Knowing where to place the antenna, how to position it, how much power it's radiating, the distance that radiated power is likely to travel, and how much of that power can actually be picked up by a receiver is probably, in many situations, going to be the most complex part of any wireless LAN administrator's job. So what is our goal? We have to understand these concepts. We can't move forward before we do. So let's look at the first one, polarization. Now, radio waves are actually made up of two fields, one electric and one magnetic. These two fields are on planes that are perpendicular to each other. The sum of the two fields is called the electromagnetic field. Energy is transferred back and forth from one field to another, in the process known as oscillation. The plane that is parallel with the antenna element is referred to as the E plane, whereas the plane that is perpendicular to the antenna element is referred to as the H plane. We're interested primarily in the electric field since its position and direction with reference to the Earth's surface or the ground will determine the wave polarization. Polarization is the physical orientation of the antenna in a horizontal or vertical position. The electric field is parallel to the radiating elements, which is the antenna element, the metal part of the antenna that's actually doing the radiating. So, if the antenna is vertical, then polarization is vertical. There's actually two different types of polarization. Horizontal polarization, where the electric field is parallel to the ground, and vertical polarization, where the electric field is perpendicular to the ground. Vertical polarization, which is typically used in our wireless LANs, is perpendicular to the Earth's plane. Notice the dual antennas sticking up vertically from almost any access point? Well, these antennas are vertically polarized in that position. Horizontal is parallel to the Earth. And what we have to think is that antennas that are not polarized in the same way are not able to communicate with each other effectively. Now you know what it means when you've got antennas that have a slightly different polarization sitting on an access point, trying to cover more or less of the frequency range. Now we're most interested in vertical polarization. That's what we're going to focus on with wireless LANs. And all of the antennas that we use need to be polarized in the same way for them to communicate with each other the most effectively. Now, there is some practical use when we're looking at polarization, and probably one of the most difficult things was what really the job that the designers of antennas for PCM-CIA cards faced. It's not easy to form antennas into the small circuit board inside of the plastic cover that sticks out of the end of a PCM-CIA card. Rarely do antennas that are built into PCM-CIA cards provide adequate coverage. Rarely do we see that the polarization of PCM-CIA cards and that of an access point being the same, which is why sometimes when you turn your laptop a little bit in a different direction, you sometimes improve reception. Whereas PDAs, which usually have a vertically oriented PCM-CIA card, normally exhibit much better reception. Also, external detachable antennas that are mounted with Velcro to the laptop computer vertically almost always show a greater improvement over the snap-on antennas included with most cards. In areas where there's a high number of PC card users, it's often recommended to orient access point antennas horizontally for better reception. And that's a lot of times why we will see with a dual dipole antenna access point, one antenna being used in a diverse fashion pointing straight up, and the other antenna being pointed horizontally to provide a mixture of signals for different types of devices. Now, one of the things that we have to understand as far as how polarization is going to function in the direct use of antennas is understanding antenna gain and beam width. Antenna gain is specified in dBi, which means decibels referenced to an isotropic radiator. An isotropic radiator is a sphere that radiates power equally in all directions simultaneously. We haven't the ability to make a true isotropic radiator, but instead we can make omnidirectional antennas, such as a dipole, that radiate power in a 360-degree fashion, but not 360 degrees vertically. RF signal radiation in this fashion gives us a donut pattern. The more we horizontally squeeze this donut, the flatter it becomes, forming more of a pancake shape when the gain is very high. Antennas, though, have passive gain, which means they do not increase the power that is input into them, but rather they shape the radiation field to lengthen or shorten the distance the propagated wave will travel. The higher the antenna gain, the farther the wave will travel, concentrating its output wave more tightly so that more power is delivered to the destination, which is where our receivers are at greater distances. Narrowing or focusing antenna beams increases the antenna's gain, measured in dBi. An antenna's beam width means just like what it sounds like, the width of the RF signal beam that the antenna transmits. Now there's two vectors to consider when discussing antenna beam width. Beam width, the vertical and the horizontal. The vertical beam width is measured in degrees and is perpendicular to the Earth's surface. The horizontal beam width is measured in degrees and is parallel to the Earth's surface. Beam width is very important for you to know because each type of antenna has different beam width specifications. So really, what is the practical use of selecting an antenna? How do we identify whether or not we're going to have a wide beam width versus a narrow beam width? Well, selecting an antenna with appropriately wide or narrow width is essential in having the desired RF coverage pattern. For example, imagine a very long hallway in a hospital. There's rooms on both sides of the hallway. And instead of using several access points all the way down with omnidirectional antennas, you've decided to use a single access point with a semi-directional antenna, such as a patch, as a good example. The access point and the patch antenna are actually placed at one end of the hallway, facing down the hallway. For complete coverage on the floors directly above and below this floor, a patch antenna could be chosen with a significantly large vertical beam width, such as 60 to 90 degrees. After some testing and site survey, you find that your selection of a patch antenna with 80 degrees of vertical beam width does the job very well. Now the horizontal beam width needed must be decided upon. Due to the length of the hallway, testing may reveal that a high-gain patch antenna must be used in order to have adequate signal coverage at the opposite end of the same hallway. Having this high gain, the patch antenna's horizontal beam widths are significantly narrowed, such that the rooms on either side of the hallway do not have adequate coverage. Additionally, the high-gain antenna doesn't have a large enough vertical beam width to cover the floors immediately above and below. So in this case, you may decide to use two patch antennas versus one at each end of the hallway facing each other. They would both be much lower gain with wider horizontal and vertical beam widths, such that the rooms on each side of the hallway are covered along with the floors above and below. Due to the low gain, the antennas may each only cover a portion, maybe half of the length of the hallway. But as you can see from this example, appropriate selection of beam widths to have the right coverage pattern is essential and may likely determine how much hardware, such as access points, actually have to be purchased for a particular installation. Another major factor that you're going to have to look at is what's known as free space path loss, or just simply path loss as it's put. This refers to the loss incurred by an RF signal due largely to simply signal dispersion, which is a natural broadening of the wavefront itself. The wider the wavefront, the less power can be induced into the receiving antenna. As the transmission signal propagates, its power level will decrease at a rate inversely proportional to the distance traveled and proportional to the wavelength of the signal. The power level becomes a very important factor when considering the link viability. The path loss equation is one of the foundations of link budget calculations, and path loss represents the single greatest